I hate myself.
All right, well, that cut off in a great way, didn't it? Let's see. We'll toss on the camera here. We will get rid of this. Let me, I guess, unmute myself here for a second. As soon as I remember how to do that. Here we go. So I think what I'm going to do, you might hear me twice now if you have both of these unmuted. I think what I'm going to do is keep myself muted here in Google Meet until anyone chimes in with a question, and then I'll unmute myself over here so we can have an actual sort of real-time chat. But otherwise, I'll just do the problems here on the YouTube stream, which there's a link to in I almost said Discord, in Notable. All right, so I'm gonna mute myself in Google Meet. All right, so I posted this list of problems in Notable here, the problem set. So we'll just go through them and yeah, just let me know if you guys have questions on them as we're going through. So we'll just get started here with problem 1. So the first problem is to find all the partial derivatives of the given function. So problem 1 here is the first function is f of xy is x to the 4th plus 5xy cubed. Right? And we want to find all the partial derivatives. Right? So hopefully you watched the video on this by now. The partial derivatives, we're just taking the derivative of this function, with respect to x, then with respect to y, and then we're just going to pretend that, one variable or the other is a constant. All right. So let's start with, say, the partial derivative with respect to x. Right. So just differentiate this function as a function of x. So 4x cubed plus 5y cubed. Right. And of course, the other notation for this is f sub x, or, you can add on the xy if you want. There's all sorts of ways to actually write that down. And then, the next partial derivative, so df dy. Now we're going to differentiate with respect to y, so we're going to pretend x is a constant. So that means this entire x to the 4th here is just gone. So I'll write a 0 here for now. And then we differentiate this part with respect to y, and we're at 15 y squared. Oops, I forgot the x. 15xy squared. Right? And so, of course, we would not bother writing that 0 usually. And just as with above, we could write this with either notation. So whichever one you want. All right. Maybe I'll keep the chat up over here. Okay. So that's basically it when we're doing partial derivatives. It's just, differentiate as we learned to in the past and, go from there. So the next function, we have z is x sine of xy. X times y. Right, so we want to differentiate this, again, with respect to x and then y. So, sorry, my partial d's sometimes get a little messed up here. So dz dx. Right, so just this one here, there's 2 parts of it that have an x, so we have to do the product rule for this one. So derivative of that first x there leaves us with sine of xy. Right? And then differentiate the second part. We have x times, we're going to get a bit of a chain rule on this one. Right? This is basically like differentiating sine of 2x. So when we would differentiate that, the derivative of the inside pops out and gives us a y, and then we have cosine of xy. Right? So if we wanted to, write this out and simplify it at all, we could say sine of xy plus xy cosine of xy. Right? And so that would be dz dx. Right. Okay. So let's look at the next one here, dz dy. Here, this is no longer a product rule anymore with respect to y, right? This would be like, 2 sine of 2y, which wouldn't require any product rule. So here, when we differentiate this, derivative of the inside is just x, so this turns into x squared cosine of xy. And that's it. Right? And just like with the last example, the first part, we could call this z sub x, we could call this one z sub y. Both notations are used. It's really a matter of convenience, which one you want to use. Sometimes one notation looks better than the other. But All right. So now the next one we got is one with 3 variables. Right, so we have xy squared e to the minus xz. Let me try and do a better job of differentiating 2 and z here. Right. So in this case, since we have 3 variables, x, y, and z, we're going to have 3 different first derivatives. Right? So we're always going to have a first derivative for each variable of the function there. All right. So let's start with x. So here, when we differentiate this with respect to x, we sort of have 2 parts, and we can group this y squared wherever we want. So perhaps we'll say group it into 2 pieces like this, right? And then we'll do a product rule with these 2. So derivative of the first is y squared times the second plus the first we leave alone times the derivative of the second, which is minus z e to the minus xz. Right. And then, you can simplify these things if you want. There's not really all that much you could really do here. You could factor out this y squared e to the minus xz, but there's not much more than that you can really do. So we'll just sort of stop there. Right. Now this one again becomes pretty easy when we try and do the derivative with respect to y, because all of this x, all of this stuff and this stuff, it's just a constant. So if we take the derivative here, really we're just differentiating this part. So we're going to get 2x, y, e to the minus xz. Right, so I'll keep the order the same. I'll leave the e to the minus xz at the end. You can put the y at the end if you want. Just make sure, it doesn't look like the y is up here in the exponent. All right, and then finally, here we have a third first derivative for z, and pretty similarly, all this stuff is a constant now out front. And so we just have to differentiate the exponential part of it. Right, so we just have xy squared times, right, well, we want to differentiate what's in here, and that gives us the minus x e to the minus xz. Right, and, of course, if you want, you could simplify it a little bit, or maybe not simplify, but just kind of rewrite it to look a bit nicer. And we wind up with that. And that's about all there is to it. So, if you can do normal derivatives, you can do partial derivatives without too much more effort, really. I guess I should take a moment to ask if there's any questions, you can type something into either of the chats here or pop in if you have a question about anything. All right. Cool. In that case, let's go ahead and do the fourth part of this example. I really wanted to include one of these because these types of functions defined in terms of integrals like this are actually quite useful in a lot of places. You often want to create functions that are like, here's the amount of distance covered from, wherever you start up to a certain point in time. So what does that look like? Oops. Cosine of e to the t dt. Right. So when we differentiate this just comes down to the fundamental theorem of calculus. If you remember how to do this, right? So when I want to do df, let's start with df dy. This is actually the easier one here. So you might remember, from 135 or whatever Calc 1 you happen to take, that if you differentiate an integral like this one here, as long as you have sort of the variable you're differentiating in the top and a constant in the bottom, then you just take that variable and plug it into the function on the inside, right? Which in this case is, if we differentiate with respect to y, we have our y up top here and we have a constant here, so we just plug that in. Cosine of e to the y, right? And that's it. Now, when we go to do the other derivative, df dx, and the problem is that the x is on the bottom, so we have to fix that. And the way we fix it is just flip the integral over, right? Same thing we would have done in the single variable case. So just flip this over. And now the same rule applies, right? So this negative sign just kind of comes along for the ride here. The x gets plugged in. And that's that. Right? So it's just the usual fundamental theorem of calculus here. These are types of functions you could be interested in say, something like probability. For example, you might be integrating some kind of probability distribution here. And, you might want to say, like, let these two, kind of your starting point and your ending point, you might want to let those be variable and say, if I change one or the other of these starting points, how is that affecting the overall probability? All right. I don't know why I'm trying to scroll this on my other computer. There we go. All right, so that's it for those examples. Next we got problem 2 here, about finding all the second partial derivatives. All right. So we're finding all the second partials of this function here. Get that right? Yeah. All right. So let's go ahead and do these, right? In order to get to a second derivative, we have to do the first derivative first, right? So, we have, say, 2 first derivatives that we need to compute. And then each of those first derivatives gives us 2 more. Right, so we have a total of 4 second derivatives, right? If we have just two variables. So, think about how many second derivatives you could have if it was a function of three variables. Right? Now, if you watch the lectures, you'll know that some of these are going to be the same for nice enough functions. But it's always worth, making sure we can get through all of them, right? Do all these derivatives. Right, so let's start by finding zx. All right, so the derivative of this is going to be, let's see, negative 2y over, all right, derivative of this is negative 2y over 2x plus 3y squared. Right? And then zy is a little more complicated. We actually have to do a decent quotient rule on this one. Let's see, we have 2x plus 3y. So that's derivative of the top times the bottom minus the top times the derivative of the bottom with respect to y is 3. And then over the bottom squared. That actually works out kind of nice. So this is just 2x, because right? these two things are going to cancel. This is 2x over 2x plus 3y squared. So I did get this one right then, right? Cool. That should be good. All right, so now that we have both first derivatives, we can now take both derivatives of each of those to get our second derivatives. Right, so zxx, this is going to be taking a derivative of this. So let me maybe write this out real quick, just so we can be a little more organized about it. I'm looking at it like this to take the derivative, right? So zxx here, sorry. Right, so the minus 2y, that's just some constant. Now I'm going to have to use basically the power rule, chain rule combo sort of deal on this. So 2x plus 3y. Here, subtract 1 from the power. I forgot to multiply by the actual power coming down. So that negative 2 comes down. And then times the derivative of the inside, which is 2. There's lots of 2's here. So this is going to be 8y times 2x plus 3y to the negative 3. Right. Of course, you can rewrite that to put the 2x plus 3y to the minus 3 back on the bottom. At this point, it's not such a big deal anymore. Right. So now let's go ahead and find the derivative of this with respect to y. So zxy. Right, so let's see, what are we doing here? We're doing d dy of minus 2y over 2x plus 3y squared. So I'm going to use the quotient rule here. That seems to be probably the best option. So derivative of the top is negative 2 times the bottom is 2x plus 3y. Right, and then minus the top times the derivative of the bottom. So we gotta, hopefully I can fit all this here. Let's see. So derivative of the bottom, we're gonna get our 2x plus 3y. Okay. That's not gonna fit. All right, we'll do this. Times, we're differentiating with respect to y. Oh, we're good. Times 3. Sorry, I thought there was more. Right, and then all of that is over 2x plus 3y squared. All of that squared. let's just go ahead and make that look a little bit nicer. We don't have to simplify it as far as this could go. Right. I wish I could actually move this camera down lower. You're looking at the top of my head the whole time. Yeah. Let's see, 2, 4, 12 plus 12y, 2x plus 3y. And then the bottom is just 2x plus 3y to the fourth. Right, and we could simplify that a little bit. We could, factor out a 2x plus 3y from the top and cancel it with 1 on the bottom. There's not a whole bunch of point to do that. Yeah. Right, so far we got these two answers. Right, so those are the two second partials where we started with x. Right. And then, we'll have the same kind of deal when we take the partial derivatives of this with respect to x. When we take this one. Let's see, 2x. Let's just copy this back down here. 2x over 2x plus 3y squared. So zxy is going to be, zyx. This is going to be the more complicated one here. So let's go ahead and get to it. So we're going to differentiate this with respect to x. So it's, of course, a quotient rule. So 2 times this one here. Minus 2x times the derivative of the bottom. So that's our 2x plus 3y. That's 1. Times the derivative of the inside, which in this case is just 2. And then all of that over the bottom squared. Right? So we write this out. We have 2 times 2x plus 3y squared minus 248x times 2x plus 3y over 2x plus 3y fourth. So there we go. All right. So now let's do the last derivative here, which is, what are we doing? Zyy. Right, so zyy, this one will be a bit easier. So I'm going to do the same kind of trick I did for zxx. Right, so I'm going to look at it like this to differentiate it. So when I take this derivative, the 2x is a constant as far as this is concerned. So 2x, now here, let me do this in this order this time. I take this minus 2 down. So 2x plus 3y, right? We're just doing the power rule on this one. And then times the derivative of the inside, which in this case is 3. Right? And, here we can simplify this if you want. I don't think we did it last time, so maybe we'll go ahead and do it this time. Get minus 12x over 2x plus 3y cubed. Right? And then those will be our two answers here. Right. So all right, any questions at all anywhere? That's definitely set off to the right spot. All right. Cool. So that's it for problem 2 here. Problem 3, right? So remember, Clairaut's theorem was this thing that said, you know, the second mixed partials are equal, right? So if we do the derivative with respect to x, then y, we should get the same thing if we differentiate with respect to y, then x. Now, there were some conditions on that, right? We had to be continuous around where we're doing the derivative, right? If that's not true, then there's no reason the mixed partials have to be the same. But if we look at this function here in problem 3, it's right in black here, but it's fine. Right, problem 3, our function is u equals cosine of x squared y. Right. So this function, it's made up of a trig function and some polynomial on the inside. So, it's a composition of continuous functions. And what we were saying in class, sort of the week before, the Friday before break, and I put this video at the start of this section of lectures as well, is basically as long as we use continuous pieces to build the function, then it's continuous. So this should satisfy Clairaut's theorem. But let's check that. So we're going to find ux, right? So differentiate this with respect to x. Chain rule says pop out a 2xy times minus sine of x squared y. Right? And then we'll do uxy. So we need to differentiate this with respect to y. So we should actually, anytime we're going to take a second derivative, we should simplify a bit. So here, notice we're going to get these two pieces again. So this is a product rule, right? So differentiate, get minus 2x sine of x squared y. Let's see, minus the first times the derivative of the second, which is, we're differentiating with respect to y this time, so an x squared comes out. Right? And just for sake of this problem, since we're trying to verify that two things match up here, let's go ahead and at least multiply this out so it looks a bit nice. Right, so we have minus 2x sine x squared y minus 2x cubed y cosine of x squared y. Right? Okay. Now we want to do uyx, right? We want to verify that that's the same as this. So uy is going to be minus x squared sine of x squared y. Right? Again, so we're just pretending x is a constant. All right. And then let's see, uyx. All right, so differentiate this with respect to x. So again, product rule on these two pieces here. Right? So derivative of the first part is minus 2x sine of x squared y. Right? And then now we're differentiating with respect to y. So minus x squared derivative in here, when we differentiate with respect to y, or with respect to x, we get a 2xy come out times cosine of x squared y. Right? and then multiply this out again, just to make it easier to see. And you should see that this and this match up, right? And that's exactly what we wanted to do to verify that Clairaut's theorem is... That was a bad attempt at a long equal sign. Those are the two things we wanted to check that are the same in order to make sure Clairaut's theorem holds, right? Any questions about that one? All right. Come on. Draw the line. There we go. All right. So let's look at problem 4 now. All right. So problem 4 here, right? We're trying to find the two partial derivatives of z, where z is defined implicitly by this equation here. Right? So, hold on. Let me check something real quick. Okay. All right. So, to do this, we're just going to basically do what we would do for implicit differentiation if it were just, the ones we did in previous semesters or previous classes, right? So let's say here I want to start by finding dz dx. Well, then what we're going to do is just take d dx of the entire equation. Right? And here I want to remember that z is a function of x and y, but x and y are independent variables, right? So they have no interaction with each other. Right? So here, when I take the derivative, the parts with respect to x, the parts that are actually going to get hit with this derivative are this, this, and this. Right? These three are the things that actually see that derivative, because those are defined, they have dependence on x. Right? So here, differentiate this with respect to x, and we get y times dz dx. Plus, here, it's x times ln y, so ln y is basically a constant, and we're just differentiating the x, so we just get ln y. That's all that's left over from that part. Here, we get a bit of a chain rule going on. So differentiate this, we get 2z, but then, z depends on x, so times dz dx. Right? And then at this point, it's exactly what we did, last semester, or again, whenever you did this stuff. All we want to do now is solve for this. Right? So let's take this and move it to the other side here. So we get ln of y is 2z dz dx minus y dz dx. And then I'm going to factor out this dz dx. All right? And then, now we just divide by that. And we're left with ln of y over 2z minus y. Right? And that's it for that derivative. Right? So not really a whole bunch to it, but virtualizing reality. Who is this? All right. So, okay. So now that we got that part, let's see this again. Let's see how this happens again with the y derivative, right? So we do this with the y derivative. Let's see, what was the... I need to rewrite this so I can actually see it. So yz... Come on. yz plus x ln of y equals z squared. Right, so if we're doing this for the y derivative, we're going to simply just take the derivative with respect to y here. Right? So hopefully, if there's any confusion with this first part, let's try this one and see, see what's going on here. And then, yeah. Right? So it should be kind of the same ideas. All right. So again, let's look at the parts that actually are going to be hit by this. So now y and z, right? Both of these depend on y, right? Of course, y depends on itself, and z is a function of y in this case. Here, the x doesn't matter, just the ln of y, and just like the other one, z squared does. Right. So let's differentiate this. Right, so when we differentiate this one, we have y times z, so we actually need to do the product rule on this. Right? Okay. So let's see. Differentiating this guy, y times z, so derivative of y is 1, so the only part that survives is z at the start. Plus, now we're going to differentiate this with respect to z, so y times dz dy. Right? Okay. So, that's it for that. That's that first part. Plus, now we need to differentiate this with respect to y. All right, well, x, because x doesn't depend on y, so we leave that alone. The derivative of the ln y, right? This is just derivative of ln, so 1 over y. And that's it for that part. Right? Equals now, this is going to actually be the exact same thing as up here, right? So derivative of 2z, right? We're going to first just think of it as, it's a function with z in it, or a function of z, so differentiate it, 2z. And then times, again, now we're going to get that chain rule step because z depends on y, dz dy. Right? And now, again, it comes down to the exact same thing as before. So I want to be able to solve for dz dy. So I'm going to move this over, and these things are going to stay over here. Right? So we have z plus x over y. And this is going to be 2z dz dy minus y dz dy. Right? Right. And just like last time, we're going to factor this out. So z plus x over y is 2z minus y times dz dy. And now we just, solve for this by taking this and dividing it to the other side. So dz dy is x, not x. Let's try that again. Z plus x over y over 2z minus y. All right. So, sorry. When you watch the lecture videos on WebAssign for the chain rule, you're actually going to see a quicker way to go about this. It's a little bit of a shortcut. I personally still like this one better, if I'm being honest. But yeah, like to me, this one just feels more like implicit differentiation. It's not a formula to memorize or anything like that. But there's all sorts of ways to do this, and again, whatever works best for you is obviously the thing to do. All right. So let's see. So we've about hit 50 minutes here. I think I'll go ahead and finish up the last one. And just remember, if you have to go, which technically class is over in like 20 seconds, but if you have to go, the video will be, hanging around on YouTube. So completely up to you. All right. But let me say here. All right. Yeah. So again, if you have any questions, pop into the Google Meet chat, or type me a message there. The link for that is in Nopal. All right. So let's finish up this last problem here. It's yeah. Wait. Can't cancel what out? There's no cancellations anywhere in any of these. Not sure. What cancellations there are. Anyway. All right. Let's see. The last problem here. So the last problem here is a bit of an interesting one. So I'll go ahead and plot this first, since that's the first step. So we have this function f of, this is problem 5. We have this problem f of xy, which is x cubed y minus xy cubed over x squared plus y squared. Right? Xy is not 0, 0. And when it is at the origin, we define the function to be 0, 0. Okay. So, let's go ahead and graph this function. Right, so we're just going to plot the, I'm just going to type the part that's above here. So x cubed y minus xy cubed over x squared plus y squared. And let's see, we only really care about this at the origin. So let's do minus 3 to 3. I just typed x 2 times. All right, cool. So Oops, I made that mistake. Remember to space your x times y's. All right, so we got a function that looks a bit like this. Let's zoom in a bit on the origin here. Right, so that's the plot of the function here. Now, if you look here, we have sort of an interesting little wrinkle going on near the origin. This function itself is nice enough, but let's see what actually happens here. So that's the plot of that function. Let's nope, not that one. This one. All right. So let's see what what's going on here. So that was part A, plotting that. Right. Part B of this, we want to take the derivative of this function, right, with respect to x and y. So actually, let's leverage Mathematica to do this for us. Save ourselves some work, right? So to do partial derivatives in Mathematica is basically exactly the same as we have been. Right, so here I want the derivative with respect to x. And here I want the derivative with respect to y. Right, let's see, is that big enough? I think that's okay. All right. So, right, so I'm gonna just copy these down real quick. Let me see if I can't get this to simplify a bit. Does that look any bit better? That's better. That's odd that the first one factored out the y. Right. So fx is going to be, I'm going to write it as x to the fourth y plus 4x squared y to the fifth minus y to the fifth over x squared plus y squared squared. Right. Fy is x to the fifth minus 4x cubed y squared minus xy to the fourth over x squared plus y squared squared. Okay. So those are the these two things are the first derivative. So actually, what we should do here, actually, let me switch back over to this. Oops. Right, so these are the derivatives. And what we want to do is we now want to take the derivative at the origin. So specifically here, these formulas are valid when the derivative is not the origin. Or sorry, when we're taking the derivative at a point that's not the origin. All right. So, all right. When we take the derivative at the origin, we now need to, use our limit definition. So, if I want fx at 0, 0, I have to do limit as h goes to 0 of f of, in this case, f of 0 plus h minus, or f of 0 plus h comma 0, there we go, words are impossible, over h. And the nice thing here is this this doesn't wind up being too complicated of a problem here. All right. So let's see. We want to do the limit as h approaches 0. Right, we're plugging in h for x, 0 for y. So, really this is just like 0 over h squared here. Plugging in 0, 0 gives us this 0, and all of that over h. Right, so this derivative is just 0. Right, likewise, you're going to find that fy of 0, 0, which we compute as, limit as h goes to 0, f of 0, 0 plus h, minus f of 0, 0 over h. You're going to find out in basically the same way that this is also 0. Okay. All right, so that's sort of this. This is where we stand. Yes, exactly, Mary. Also, I have to be able to sort of know that you're one of my students. So having an alias doesn't help. I recognize who you are in the chat there. I'll respond. Anyway. So now that we have those, let's look at the last part here. We want to take the mixed partials at the origin. Right? So now we want part D here. We're looking for f of xy at 0, 0. Right? So the second partial fxy, 0, 0. So we're going to use these formula we found up here. Right, because before we take this limit, we're not at the origin, so we can plug all that stuff into these derivatives that we found, and then do the derivative, or then do the limit. Right? So here, in terms of a limit, this derivative is fx at 0 plus h, 0, minus fx at 0, 0. Oh, sorry, we're doing fxy. I did this backwards. 0 plus h. Right, over h. Okay. So again, this is it's the derivative with respect to y of fx. So right, let's go ahead and if we write this out here, well, let's look at this. So we're plugging in 0 for x and h for y here. So 0 for x means all this stuff is 0. H for y actually gives us something here. So we get what we're going to wind up with is minus h to the 5th over h to the 4th. Okay. Now fx at 0, 0, that's what we did right here. That's just 0. And this is over h. So what actually is going to happen when we simplify this is we're going to get negative 1. And so that derivative is negative 1. All right. Okay. If we do the same thing then for fyx at 0, 0, this is going to be limit as h goes to 0 of fy 0 plus h 0 minus fy 0, 0 over h. Should separate these a little bit. Okay. So let's fill in a little bit of these gaps before we scroll back up here. Right, so these two things we already know from here. So now we're plugging in h comma 0 to this function. Right? And when we do that, the all the stuff with y's goes away up top, and we're just left with x to the 5th, and then we're going to get an h to the 4th out of the bottom there. And so we're going to have h to the 5th over h to the 4th. But this limit this time is actually going to be, h to the 5th over h to the 5th when we simplify that. And so we're going to get 1. So here we get a 1, here we get a -1. So we have, -1 is fxy at 0, 0. But that's not equal to the derivative in the other order. Right? So an important question there then is that a failing of Clairaut's theorem, right? The one that the second partials should be the same. And the answer is no, it isn't. Right? And the reason for that is, the condition we need is that the first partial derivatives are continuous at 0, 0. So to see whether that's true, we can look at the graphs of these derivatives here. Let me bring Mathematica back up. So let's make this a little easier. Call this f. We'll just do this. And then we'll do plot dfx. X goes from -1 to 1. Y goes from -1 to 1. Right. What have I done? Oh, right. Right, maybe that'll help. Or not. All right, we'll just do this then. I'll have to double check what I've done. All right then. Oh! Multivariable function. I need plot 3D. Sorry. I'm sure all of those that I did would work. So if we look here, right, if we look at the origin here, we see something like, see how these are very kind of sharp corners here, where this all meets up? This has to do with, remember back when we were learning, like, when is a function differentiable or not? And, absolute value isn't differentiable. It's the exact same idea here. This corner is going to cause an issue. Same place, Maya. I'm going to go back through the list of problems in just a moment here. So you can just hang out right here. I figured I'd go through the explanation of this problem one time and then just loop back around. All right. Yeah, and then if we plot the derivative of this with respect to y, you can see the same kind of thing happens. Right, so again, we get that kind of like really sharp corner right here. Right, and that really sharp corner makes it not differentiable. All right. Oh. That was round 1 of these. So I'm going to take 2 minutes here, and then I'll be right back, and we'll go through the problems one more time. So give me 1 second here. All right. Now we go for round 2. Where'd the camera go? Okay. So, all right. Let's go ahead and go back through the problem list here. Let's see. Put this back over here for now. All right, so I'm gonna unmute myself in the Google Meet call real quick, just to make sure everyone hears me say it. So if you are listening to both, you might want to mute one of them. All right, just wanted to make sure you all hear. So if at any point you guys have questions, the ideal thing would be just unmute yourself here on on Google Meet, or send a message to either the YouTube or the YouTube stream or the chat in here, and we'll answer your question. All right. So I'm gonna mute myself again here in Google Meet so you don't hear me twice. Yep. All right. Cool. So let's go ahead and get to this again. All right, let's see. Looks like I had just enough pages here, so we should be good. All right, so the first problem here, we're just doing some simple partial derivatives. So let's go ahead and get to it. Right, and if you were here for the first round, feel free to stick around for the second go through of the problems if you want. Completely up to you. Right. So let's see here. So we're finding partial derivatives in the first problem. Oh. All right. I'll wait here for like 5 more seconds. It should be good already, but just want to make sure it picked it back up here. I have the stream up. Okay, I just did that head turn to see if the live stream was good. All right, cool. All right, so let's go ahead and get back to our problem here. What were we doing? We're trying to find the first partial derivatives of this function, x to the 4th plus 5xy cubed. So partial derivatives here, all we're doing is just, kind of need that program up. We're just taking the derivative, pretending, one variable, the other is a constant. So df dx, we're going to differentiate this. Okay. We're going to, for this derivative, pretend that y is a constant and take the derivative with respect to x. So we get 4x cubed plus 15 xy, oops. I got ahead of myself. Plus 5y cubed. Right, so the only parts that get differentiated are the x to the 4th and just the x here. All right. Now when we differentiate this with respect to y, right, here, this part has no y's at all, so it's just gone. Here, we're going to pretend that x is just a number and differentiate this. So we get the 3 comes down, so we get 15xy squared. That's it. Right? And, we could call this fx. We could call this one fy. We could add on the x and y if you want. Any of these notations are fine, really. It's up to you. Right. So that was the first one. Let's look at the next one. So we got z equals x sine of xy. All right, so this one's a little more interesting. When we differentiate this one, so I'll switch to the other notation here. Right. When we differentiate this, now here again we have x showing up in 2 places. So this is a product rule. Right. So we have our 2 functions here. So derivative of the first times the second plus the first we leave alone times the derivative of the second. When we differentiate the second one, this y comes out through the chain rule, right? Just like if this were, sine of 2x, basically, the 2 would come out. So we have times y cosine of xy, right? And actually, there's not really anything else to do here. Not much else to do. Right? So how about zy? Well, now when we're differentiating this function with respect to y, this function here, it only has a y in one spot right here. So this is no longer a product rule at all. This is kind of like differentiating 2 sine of 2y. So, all right, we get x times derivative of this. The x comes out because it's the derivative of the inside times cosine of xy. Right? And if you want, you could skip this first step here and just immediately write x squared. There's no reason not to, really. All right. All right. Let's see. Problem 3 here. Here we have a function of 3 variables. Right, but not much changes. Not much changes. Or anything, really. Right? So here, when we want to do the derivative, right, we want to, again, this time, when we do df dx, I didn't mean to write that in blue, but it's happened now. When we do df dx, we're pretending both y and z are constants. So here, I'm going to group this into 2 pieces again, because there's 2 pieces that have an x in it. So let's go ahead and do this derivative. So derivative of the first is y squared, e to the minus xz, plus, we leave the first one alone, times the derivative of the second. Right? So when we differentiate the second part here, a negative z comes out, and then that's it. I wanted to write xy, xz. Right? So you can, if you want, simplify this a bit. I mean, we can factor some stuff out if you want. Like here, you could rewrite this to be this. Actually, that's it. It's kind of up to you how much you want to factor and simplify this. The most important thing is that, you get yourself to here, where everything's been differentiated. And at this point, it's just algebra, so I'm not particularly worried about it. Yeah. Right. Now this becomes a lot easier when we go to do the next derivative, df dy. Right? And that's because this is the only part that has a y in it. So that means all of this stuff is just a constant. So when we differentiate this, we're really just differentiating y squared. So we get 2xy e to the minus xz. That's it. Right? Just differentiate the y squared part, and there we go. All right. Last one here, df dz. Right? So we're going to differentiate this with respect to z. This part here is still a constant as far as z is concerned, so we don't need to worry about that. When we differentiate, so differentiating this part, we're going to get something like this happening. The minus x comes out. We have xy squared minus x e to the minus xz. And so, if you like, this is minus x squared, y squared, e to the minus xz. Right? And again, you know, as usual, the most important thing isn't simplifying complicated derivatives, it's just making sure that you know, you get all the important pieces there. You've applied the product rule correctly or the chain rule correctly. You've done the derivatives correctly. That's, you know, the biggest issue here. Right. So any questions about those? All right. I don't know if it's the same for you guys. Like, you know, you're not supposed to touch your face now. But I kind of feel like now that I can't do it, my face itches more. It's really weird. Sorry, completely off topic here, but just have to rant about it for a second. Anyway, problem 4. Right? So problem 4, this one is a little more complicated looking of a function, but really it's probably one of the easier examples we have here, actually. So this function is defined as an integral from x to y of cosine e to the t dt. Right? So these types of functions are actually quite important, defining a function in terms of an integral like this. One common way this is actually used in physics, for example, is to say, all right, you know, here's my starting point. I want to, say, find the distance traveled from my starting point till whatever time t. So you would set up your function of t as an integral from, say, time 0 to time t of, you know, whatever you need to integrate. In a case like this, you could do something like, you know, maybe this function on the inside here is a probability distribution, right? So this function here would say something like, you know, what's the probability of landing between these two numbers? Whatever that should mean for your particular probability distribution, right? So integrating those is how you find probabilities. All right. And, you know, setting it up as a function like this and doing the derivatives, you know, that could let you know how these things are changing. Anyway, let's go ahead and take the derivatives of this. Right, so the derivatives of this is just a fundamental theorem of calculus, right? So let's start with the easier one here, df dy. You know, when we're doing the derivatives of these integrals here, fundamental theorem of calculus says if you have your variable up here and a constant down here, then when you take the derivative of this thing, you're just going to take this variable right here and plug it in there. That's it. So this is cosine e to the y. Right? Because again, x is a constant as far as y is concerned. Right? When we want to do this derivative with respect to x, so our variable is in the wrong spot here. It's in the bottom instead of on the top. So to fix that, we just flip it over, right? So this is negative y to x cosine of e to the t dt. Right? Remember, when we flip the bounds of an integral, we get a negative sign. And so when we do this derivative, we get negative. Negative cosine. That O is terrible. Cosine of e to the x. Right? And that's it. Right, so again, not a particularly difficult problem. It might look a bit trickier, but it's not that bad. Draw the line, please. All right. So that's problem 1. Hopefully nothing too bad. Problem 2 is find all partial derivatives of, sorry. I wrote find all of the section partial derivatives. That's supposed to say find all the second partial derivatives. Right. So we want to find all of the second partials of this thing. Okay. So let's go ahead and check that out. So, when we do the derivatives, we're going to get zx and zy, right? We take the x and the y derivative, and each of those get new derivatives. Right? Zyx, zyy. We can do the x and y derivative of each of those. Okay. So let's go ahead and do the derivatives here. All right. So we need to start by finding both first derivatives. So zx, right? This one's not too bad. We're doing the derivative here. I think this makes a lot more sense to look at it like this. But again, completely up to you how you want to go about this one. When you do this, right, you're going to basically wind up with minus 2y over 2x plus 3y squared. This is what you're going to wind up with at the end of the day, because this minus 1 is going to come out front. This 2 is going to come out from the chain rule. So there's the minus 1 and the 2 right here. This power goes to negative 2, which puts it in the bottom and gives it a square. Right? Right. So now let's find the 2 second partials with respect to x. The zxx and zxy. Let's do that, and then we'll do the y stuff. Right? So zxx, this one is pretty straightforward, right? I'm going to do the exact same thing I just did. Right? So I'm going to look at it like this again, and I'm going to do my derivative. So here we have minus 2y. The negative 2 comes down. We have this part. The power goes down by 1. And then we multiply by the derivative of the inside, which is 2. Right? And so this all simplifies to, let's see, 2, 4, 8. Yeah, positive 8y over 2x plus 3y cubed. Right? So that's it for that derivative. Nothing super tricky. Let's look at zxy. So here, actually, I want to keep this on the screen for the moment. When we're doing this one, there's a y in the top and in the bottom, right? So I can still do this trick here, and it'll make it a product rule. But maybe in this case, it'd be nicer to do the quotient rule. It's, again, completely up to you. Here, when we did zxx, we didn't really need a quotient rule. Just like when we found zx, because there's no y in the top, or no x in the top, we didn't really need the quotient rule. But here, it's a good idea to use it. So let's go ahead and differentiate this with respect to y. So derivative of the top times the bottom minus the top times the derivative of the bottom. We have 2x plus 3y times 3. And that's all of that over the bottom squared. right? And, we can, if you want, we can clean this up a little bit just to make it look nice. It's completely up to you, though. Let's see, minus, minus, so this is plus 2, 4, 12. Plus 12 of these guys. Okay. And the bottom is 2x plus 3y to the 4th. What is going on here? Sorry. My phone is really loud on my desk. Right? So those are 2 of the 4 second partial derivatives. My hand motions keep getting cut off, and it's really odd. Oh, that's actually as far down as the camera goes. All right, that's fine. It's a little bit better. All right. So now that we've done that, let's see. Actually, I got the function over here. So let's do the derivative of that function with respect to y now. So zy, right? We're differentiating y over 2x plus 3y. Sorry. Right? So here, we're going to use the quotient rule, right? So derivative of the top is 1 times the bottom minus the top times the derivative of the bottom all over the bottom squared. Right? So here, some stuff actually cancels out. Right? If we look at how this works out, we get a 3y, a minus 3y. Right. I need to set up a hotkey to mute my mic so I don't have to fish for my mouse every time. All right. So this is going to simplify our derivative a little bit here. We're going to have 2x over 2x plus 3y squared. Right. And now we need to take the 2 second derivatives of this thing. So zyx, we're going to do the derivative of this with respect to x. Now, there's an x on top and bottom here, so we get to do the quotient rule again. So derivative of the top is 2 times the bottom minus the top times the derivative of the bottom, which is going to be 2 times 2x plus 3y times 2. And again, all this over the bottom squared. So, again, if you want, you could simplify this a little bit. G for 8x, 2x plus 3y. All that over 2x plus 3y squared. Right? So that's our second mixed partial there. And now we're going to find zyy. Right? So here, we're taking the derivative of this thing up here with respect to y. So a nice thing here is there's no more reason to really do the
Dr.
quotient.
Burkhardt?
Yep. Oh, right. I need to unmute over here.
Shouldn't, for the last one, shouldn't the denominator be to the 4th?
It absolutely should. This was supposed to be squared. Yep, that's right. Thank you.
Okay, thanks.
All right. I was too much in a hurry to get the quotient rule over with. chat back up there. Cool. All right, so ZYY, as I was saying, this one here, there's no Y up top, so we can kind of do the shortcut we did here for ZXX, which is pretty nice. Right, so I'll write it out here. Let's see. And at 2x plus 3y to the minus 2. So this 2x just comes along for the ride. This negative 2 comes down. 2x plus 3y. Here, the minus 2 goes up to minus 3. And then times the derivative of the inside here, which is 3. It's on the next. This is 2 minus 4, negative 12. X to the 2x plus 3y is 3. Or, if you want, you can put that stuff back on the bottom. That looks better to you. And, you know, both of these, XX has this cube on the bottom, YY has this cube on the bottom. These ones, the two mixed ones, they have this fourth power on the bottom, but you can also, if you really want to factor and simplify as much as possible, you can factor out this 2x plus 3y on the top and cancel one of these on the bottom. So they're all like, you know, third power on the bottom if you want. Again, it's just a technicality, a nicety. If you want it, no reason you have to do it. All right. So, just give myself a second to breathe here. Any questions? So, all right. So, problem 3 here. This is all about verifying Clause's theorem for this function. Right, so this is much less work than the last one. Here we only need 2 of the mixed partials, or sorry, 2 of the second partials. And it's the mixed ones, the uxy and uyx, right? So it's important to remember what that theorem is saying. And it's saying that, you know, we should expect those 2 second partial derivatives to be equal, basically as long as they're continuous. So let's go ahead and find the 2 mixed partials that we're looking for. So ux here, do this derivative. We're going to have negative 2x sine x squared y. I forgot a y here. Right, derivative of the inside here is 2xy. So we get the 2xy coming out, the minus because derivative of cosine is sine. And then let's go ahead and just write down uxy. Right, so this is a product rule between those two. We get minus 2x sine of x squared y. And then plus the first part. 2x. Oops. You know what? Let's just put the minus right here. So the first one times the second. Derivative of the second is, let's see, with respect to y is x squared cosine x squared y. Right? Right. Now, since we're trying to check that 2 things are equal here, let's at least multiply this out. You don't have to simplify it as much as possible, but let's at least multiply stuff out. It'll make it a lot easier to see. Though, this one might not be particularly difficult to do regardless. It's always a good idea. So now that that's done, let's find uy. So here we're going to differentiate this with respect to y. So the x squared comes out, we get a negative because of the cosine. And that's it for the y derivative. So now we take the derivative of that with respect to x, and just like last time, we have a product rule. X. Right, so derivative of that first part is minus 2x sine of x squared y. And then derivative of the second part, here we have minus x squared times, let's see, derivative of the inside with respect to x is 2xy. And cosine of x squared y. Right? And, again, you can probably already see the answer at this point. So, like I said, it's really just a convenience factor to double check everything. But if we multiply this out, two x cubed y cosine of x squared y. So as we were supposed to have, these two are in fact equal to each other. Right? And that's what we expected, that these two are equal. And again, we can verify that we should actually expect that by if we look at these guys here. Oh, they're nice. If we look at these, they're nice and continuous. So, by the theorem, we should expect that that the second partials commute, right? So, meaning like we can do x then y or y then x and get the same thing, right? And if you happen to get here in time for the explanation of problem 5 earlier, you'll have seen something where that doesn't quite work out, right? Okay, so any questions about this one? So let's get on to, all right, well, pink line it is. Let's get on to the next problem, problem 4. Right, so here we have that z, is implicitly defined as a function of x and y by this equation. Right, so I'm going to write over here that z depends on x and y. Right? So, depending on how far ahead in the lecture you've gotten, you may have seen how to do this with the chain rule, which we'll do tomorrow. But the way I'm going to do it here is kind of the way I think is better regardless, because one, it doesn't involve kind of just memorizing a formula. But two, it follows literally the exact same process you would have done, in Calc 1 or 135, right? So when you want to find dz dx, we just take this equation right here and differentiate every piece of it with respect to x. Right. So when we do that, it's a good idea to think about what parts of this actually get differentiated, right? And it's all the parts that have any dependence on x, anything to do with x. So this has dependence on x. This has dependence on x, kind of obviously. And this does. So everything else, basically anything with y's or actual constants, are treated as constants. So when I differentiate this, the first part, nothing happens with the y. Derivative of z with respect to x is, well, this is the best we can do. Just say the derivative of z with respect to x. Right? Plus, right? This part here, this is x times ln of y. Well, again, that whole ln of y, all this part is just some constant times x. So this may as well be like 4 times x. So this is just ln of y. That's it. Right? It's just the derivative of x. Over here, z squared, well, we're going to differentiate it, as we normally would, 2z. But then since there's a z there, kind of the chain rule pops out with a dz dx. Right? So that should kind of remind you of the exact same thing you would have done last semester, or again, whenever you took your first calculus class. Right? You probably would have done the same thing. Just now, there's more letters floating around. That's really the only difference. Right? So what we want then is we want to solve for this thing. So what we're going to do is take this part and move it to the other side. It's y, x. Right? And then, well, we're trying to solve for this, so let's factor it out so we can actually get it by itself. Right, so now we're going to take this stuff and move it to that side. And I think I can fit the here. dz dx is now going to be ln of y over 2z minus y. Right? And that's that. That's it for this. Oops. That's it for that partial, that partial derivative. Right? So hopefully you can see here, it's kind of exactly the same thing, right? It doesn't really differ at all. Again, aside from having more letters. Right? So let's look for dz dy now. Right, so here we're going to do the exact same thing. Right. So, we need a drink here. All right. So, let's look again at what parts of this actually get hit with the derivative. So the y does, because it's derivative with respect to y. The z depends on y, so that's going to get hit. X, nope, has nothing to do with y, so skip it. ln of y is going to get hit, as is the z squared. So here we actually do have to do a product rule, right? Because both of these things depend on y. So, all right, no big deal though. Derivative of the first is 1 times z plus y times the derivative of the second. Okay, so we just get a dz dy. No, again, nothing really different. Plus x is a constant here, so derivative of ln is 1 over y. It's x times y. All right. And this one, we get basically the exact same thing. 2z dz dy. Bad. Right. And so just like before, we're going to take this part, move it to this side so that we can group the derivatives together. We get z plus x over y is 2z dz dy minus y dz dy. This is 2z minus y dz. Right. And now we're going to just take this piece and divide it over here. Right, so just like last time. Get dz dy is z plus x over y divided by 2z minus y. And that's about all there is to it. Right, so if you remember how to do the implicit differentiation from last semester, or again, you did it, it's basically the exact same thing. Now, again, when you watch the lecture videos for tomorrow on the chain rule, you'll see that there's a shortcut to do this, or at least somewhat of a shortcut, depending on your definition of a shortcut, that can possibly simplify it for you. But yeah. All right. So now let's set up for the next problem here. So the next problem here is a bit more interesting. We're looking at a somewhat strange function. We're looking at this function f of xy equals, right, we have x cubed y minus xy cubed over x squared plus y squared. And this is as long as we're not at the origin. Right? If we're at the origin, then the value of the function is just 0. Right? So we'd have to define this function separately at the origin because we can't plug in 0, 0 here. But that's fine. So let's go ahead and look at sort of part A of this is saying, or I guess part 1 of this is saying, well, graph this function. All right, so let's look at it. So let me bring up Mathematica here. Here is a plot of the function. I haven't bothered doing the, like removing the box, placing the axes at the origin here, just to make this simple. When we do plot a function of two or more, or of two variables here, remember we want to use plot 3D because the graph of this is going to be a 3D surface. All right. So when we plot this, obviously looking at the definition of the function, the interesting part is at the origin. So I just did a little square around the origin. You can see the origin here is at this crossing. And if we look at it, there's not too much going on. It's kind of got this interesting little X shape here going on at the origin. I don't know if you can see that. But this graph itself, this function itself, there's not a whole bunch of issue with it. So, all right, let's see what happens. So what we want to do in part 2 of this is we want to take the first partial derivatives, right? So let's take those partial derivatives. So let me call this thing f. And I want to find d of f with respect to x. Right? So I get this. Maybe let's simplify this a little bit to make life easy, or to make this look nice. Right? So here's our first derivative. We could do this by hand, but it wouldn't be terribly fun. So we'll skip doing that by hand. So, all right, so there's our first derivative with respect to x. Let's do this with respect to y. So dfy. And we have these guys. So these derivatives here, they're valid as long as we're not plugging in the origin, right? Because this is how... This expression right here is how the function is defined away from the origin. So when we differentiate it, these derivatives are valid away from the origin. So I'm just going to copy these over here real quick. In fact, let me just switch back over. Right. So what we have for part B, what we found is that fx is x to the 4th y plus 4x cubed, x squared, y cubed, minus y to the 5th over x squared plus y squared, and fy is x to the 5th minus 4x cubed y squared minus xy to the 4th, all that over x squared plus y squared squared. Right? Oh, I switched to the wrong one. I meant to do this one. All right. So these are the two first derivatives away from the origin. Okay. Now, when we want to do the derivative at the origin, we have to actually use the limit definition, right? So we're looking here at fx00. This is limit as h goes to 0 of f of 0 plus h, comma 0, minus f of 0, 0 over h. Right? So when we plug this stuff in, we're plugging in h comma 0 to fx, so to this thing. So that means this part's gone, this part's gone. Oh, sorry, I'm looking at the wrong thing. Sorry, we're doing this one. So the top is gone, and the bottom is just h squared. So we actually have 0 minus 0, h, and so this is 0. Likewise, when we do the derivative with respect to y, zero plus h minus f of 0, 0, h. Similarly, you're going to find that this one is also just going to be 0 because the two things on top are just going to wind up being 0. Right? So, these first derivatives are still 0. Okay, cool. Let's see if Claraut's theorem works for this, right? So what we're going to do now is look at, well, what is f of xy? Or fxy of 0, 0. So this one, right, we're going to do fx of, 0, 0 plus h, minus fx of 0, 0, h. Now, when we plug in 0, comma h into fx, into this, we're going to get negative h. Right? So I'll let you kind of work through that. But when we plug it in, this part's gone, this part's gone. This is minus h to the 5th. The bottom is h to the 4th. So we're going to end up with this. Right? We know this is 0. And so this derivative is negative 1. Right? If we look at fyx of 0, 0, right, so this one's going to be fy of 0 plus h, comma 0, minus fy of 0, 0 over h. When we plug in h for x and 0 for y here, we're going to get h to the 5th over h to the 4th, which just winds up being h again. We have h minus 0 over h. But this one's 1. So here we go. Two different answers. And we checked both of the mixed partials here. So the question is, does that conflict with Claraut's theorem, right? The one that says mixed partials should be equal. So the fact that I'm asking this question should mean no, there's not a conflict. The question would be, well, why not? And that comes down to, let's look at the graph of these things. So let me switch back over to Mathematica here. let's look at the plot of this thing. Once you see it for one of these, kind of what happens in the other one will make a bit more sense. What have I done here? I'm just going to copy this. All right. So if we look at this graph here, there's something kind of more serious going on than what was going on in the original graph here. Like we could see everything is nice and smooth here. You can kind of see this X pattern. And what that was doing is, you know, when we took the derivative, that X pattern now turns into this folding that's going on here. This kind of like sharp folding, right? And, you know, if we think back to like, well, when is a function differentiable, right? The slope has to make sense, right? And, you know, we need to think like, well, all right, when I take this function here, this is still nice and continuous. But when I try to take the derivative of this is when we run into the problems, because those derivatives are what we need to be continuous. And if we look at the graphs of this, you know, there should be some kind of like remembrance of a absolute value going on here. So there is some issue at the origin here. And likewise, if we try to plot the derivative with the yx derivative, we see we still get this kind of folding, this corner at the origin there. And that's what's causing Claraut's theorem to fail. Is when we take the second derivatives of this. So actually, let's see how nice of one we can get. Let's see. So the second derivative will have df. Let's do x, one derivative of x, and one derivative of y. All right, so we got whatever that is. Let's take a peek at the plot of that. Yeah, so you can see here, something's gone horribly wrong near the origin. And that's why our derivative's not existing. So I think I mentioned on Friday before break, if you start having functions that look like they're pinched or torn, that's when you lose continuity. This is that kind of thing. Like right here, it looks like this is pinched at the top right here. I don't know if you can kind of tell that. And if you look at this from the bottom, there's kind of a pinching and tearing going on down here. And that's because this function isn't defined there. There's some kind of discontinuity. All right, so I only went 8 minutes over class time. But this VOD should remain on YouTube here. Hopefully that's the case. Everything that's what things are supposed to be set up to do. But yeah, so hopefully, you know, hopefully doing the session like this seems useful. I think I might kind of maybe rearrange the times we do this at. You know, to try and include some of our friends and classmates from the other side of the world. So I'm going to send out a survey about that probably later today. And I might do something where, like, you know, I do a session of this at noon and then another session at maybe 8 p.m. or something like that. 8 or 9 p.m. because that'll be, if I remember this correctly, that should be 8 or 9 a.m. in China at least. So maybe 10. We'll see what goes on. But yeah, so those are all the problems. If anyone has questions, let me know. Otherwise, I think we'll call it there for now. Hope you're all doing well. Yeah. I will see you next time. Take care.